Aromatic reactions is a heavy chapter. We need to understand sterics, electronics in order to understand the key reactions. So in today's video, we're going to talk about electron withdrawing and electron donating groups and how that impacts reactivity. And finally, we'll look at Friedel Crafts and electrophilic aromatic substitution, as well as SNAR reactions. So let's get started. In order to really understand those reactions, we're going to look at the electronic structure of the ring, depending on whether that ring is attached to an electron withdrawing or electron donating group. And then we'll look at Friedel Crafts and electrophilic aromatic substitution. And finally, we'll look at SNAR. So let's start with the electron withdrawing group. Electron withdrawing groups are known to be deactivating. And these electron withdrawing groups are going to be things like cyano, acyl, this could be anything here, amido, doesn't matter. Anytime that we can draw like a resonance structure where the electrons are coming out of the ring, that's going to be deactivating. Let's look at why. So if we have this acyl group, what I see is that this acyl having this double bond is an electron sink. What that means is that I can take the electrons that are in this bond and push them through the carbonyl up to the oxygen. What that means is that I've taken those electrons out of the ring and I've given them to the oxygen. So now I've made this double bond and I put this lone pair onto oxygen, giving it a negative charge and this carbon a positive charge. I can continue to push electrons around the ring. I can see that these can come and meet that positive charge. This is going to create a new resonance structure where that oxygen is still negatively charged. I still have this double bond here, but now I've moved my electrons to have a positive charge now at this carbon. I can continue to push electrons all the way around the ring so that then I can have a third resonance structure where again that oxygen is still negative. I still have this double bond, but now I've made a new double bond here and the positive charge ends up on this carbon. These resonance structures help us to understand the overall reactivity of the compound. And so if I'm looking at the benzene with an electron withdrawing group, I see that there's positive charge on this carbon, and there's positive charge on this carbon. This is going to tell me about their reactivity. If I'm looking at electrophilic aromatic substitution, where the aromatic ring is a nucleophile, I see that this is going to be meta-directing because I can't have a nucleophile with a positive charge. That means that in electrophilic aromatic substitution, I'm going to react here where there's not a positive charge. But if I'm looking at SNAR, these are actually going to be orthopara-directing because in SNAR, the aromatic ring is the electrophile. So the directing effect kind of depends on what it is that we're looking at. Let's now compare and contrast this with the electron donating group. Electron donating groups are known to be deactivating. These are going to be things with lone pairs, like amines, alcohols, ethers, even esters if they're connected at the O. Additionally, these are going to be alkyl groups because those donate electron density through hyperconjugation. These are going to be activating because they're pushing electrons or electron density into the ring. And so if I look at this lone pair on the oxygen, I see that I can push these electrons towards the ring and then onto this carbon. Let's go and create a resonance structure that looks like this, where these electrons have ended up here. And I still have my double bonds. This is going to give the oxygen a positive charge and this carbon a negative charge because it has a lone pair. I can continue to push electrons from the lone pair onto the next carbon. And what this is going to do is it's going to put that negative charge here. I can continue to push these electrons onto the next carbon. I still have my OH plus. I still have this bond, but now I've made this double bond and pushed this lone pair here. So this is kind of similar to the electron withdrawing, but different. In the electron withdrawing, we saw a positive charge at these positions. Here, if I look at the resonance structure, I actually have negative charge at these positions. And so if I'm thinking about a ring acting like a nucleophile, this is going to be orthopara-directing when the ring is acting like a nucleophile, like an electrophilic aromatic substitution. And it's going to be deactivating in the SNAR. In order to do SNAR, we need electron withdrawing groups. And so this can even cancel out the effect of SNAR and make it really difficult to do SNAR. But we'll just say for now that it's meta-directing for SNAR, because we need that carbon to be electrophilic, which is only in these positions. Let's look at what this means for reactivity. We're going to start with the electrophilic aromatic substitution. This is also the Friedel Crafts. Here, the aromatic ring is a nucleophile, and we saw that the electron donating group directs orthopara, and the electron withdrawing group directs meta. So let's look at a general mechanism. Here we're going to see that the aromatic ring is the nucleophile, and we're going to have some electrophile. Reactivity-wise, electrons from one of these double bonds are going to come and grab the electrophile. It's going to create a new bond to the electrophile and leave a positive charge on the neighboring carbon. These electrons left the carbon to grab the electrophile. They're here. So this neighboring carbon has a positive charge. We're always motivated to regain aromaticity. So what we see happen is that a deprotonation event happens to lose the hydrogen and regain aromaticity. So that's going to reform our double bond, and we're going to have the electrophile added to the ring. The most common mechanism that we're going to see using this electrophilic aromatic substitution is the Friedel Crafts alkylation and the Friedel Crafts acylation. In this case, we first have to activate the electrophile. We're going to use some type of alkyl halide and a Lewis acid. We need the Lewis acid in order to activate the electrophile. And so what we see happen here is that the halide of our alkyl halide attacks the Lewis acid, and this is going to create a Lewis adduct. This Lewis adduct is going to be negatively charged on the nitrogen and a positive charge on the chlorine. Chlorine really wants to be with this Lewis acid, so we see that the electrons from this bond break to go onto the chlorine. This is going to give us a carbocation, and it's going to give us the chlorine Lewis adduct. This is carbocation, so everything that we've seen in SN1 or any type of carbocation chemistry applies here. So this can rearrange to form the most stable carbocation. Now let's look at what happens when we add the aromatic ring. What we saw in the general mechanism is that the aromatic ring attacks the electrophile. In this case, the carbocation is now the electrophile. So we see electrons from the ring come to grab that carbocation. This is going to generate our intermediate. I have methyl, methyl, ethyl. I have my H, and I'm going to have my neighboring carbocation. So this is going to generate the same intermediate that we saw here. But now what's actually going to grab that H is our Lewis adduct. So the electrons from this chlorine-iron bond are going to come grab the H so that we can regain aromaticity. This is going to lead to our final product, and then we're also going to produce HCl and regenerate our Lewis acid. So this can actually participate in another round of chemistry, another round of activation of our electrophile. And so this is the mechanism for Friedel Crafts. The only difference between the alkylation and the acylation is the electrophile. So let's look at that really quick. If we have a Friedel Crafts acylation, here we start with an alkyl chloride, and we react again with our Lewis acid. So we're going to see the same first step, where the chlorine attacks the Lewis acid, and we make a very similar looking Lewis adduct. But in this case, the electrons are going to come down from the oxygen to kick off the chlorine to make this ion. And here we don't have a formal carbocation, so this is much more stable than C+, so than carbocation, and it doesn't rearrange. We're going to be electrophilic at the carbon, so at this position, but without rearrangement. That's the only difference between the alkylation and the acylation. So in the alkylation, we want to watch out for carbocation rearrangement, but in the acylation, we make this ion and we're good. Now let's look at the SNAR. This is nucleophilic aromatic substitution, and here the aromatic ring is the electrophile. We need a pretty deactivated ring in order to do this, and we need a good leaving group, like nitro or fluorine. We see that electron donating groups direct meta, and electron withdrawing groups direct ortho para, but these can also deactivate the ring, and so we always kind of focus on the electron donating group can deactivate the ring, and so we focus on the electron withdrawing group. Let's look at a general mechanism. So here we're going to have a nucleophile that's going to react with our aromatic ring, which is the electrophile. Here I have two possible leaving groups. I have a fluorine in the meta position, and I have a fluorine in the para position. Here I see an electron withdrawing group, so this is going to be directing ortho, and it's going to be directing para. I don't have anything in the ortho group, so I'm going to react with this fluorine. What I see here is that the nucleophile is going to attack the carbon, and electrons are going to flow to the electron withdrawing group. That's going to give us an intermediate that looks something like this. We're going to have the fluorine that we didn't react with. We're going to have our nucleophile, our leaving group, and we push the electrons. Here's our electron withdrawing group to put a lone pair here next to the electron withdrawing group. We put the electrons next to the electron withdrawing group because there's a stabilization effect from the electron withdrawing group. Now we're interested in regaining aromaticity, so we have to eliminate our leaving group. So I'm going to take these lone pairs and I'm going to push them back, but now I'm going to give them to the leaving group. What we're going to end up with is the same type of structure, but we've now eliminated our leaving group. So I'm going to have my fluorine that I didn't touch. I'm going to have my nucleophile, and then I'll have an F minus. And so this is the general mechanism of an SNAR. Let's look at another example. So here I have kind of a lot going on in the ring, right? I have two electron withdrawing groups. I have a nitro and I have a carbonyl, and I have two possible leaving groups. I'm going to try to apply the same logic. I see that this fluorine is ortho to two electron withdrawing groups, and this fluorine is meta. I'm an SNAR, so I'm activated in the ortho and para positions. That means that this fluorine is going to be the best leaving group, and I'm not going to touch this one. So for my mechanism, I'm going to take my lone pair of electrons from the nucleophile. I'm going to push to the carbon, and then I'm going to push up through the electron withdrawing group. I still have my nitro. I still have this fluorine, but now I push my electrons up to oxygen, and I've formed a bond with the nucleophile. Now these electrons are going to come off of this negatively charged oxygen and out through my leaving group. Here I've regained aromaticity by reforming that double bond. I still have this metafluorine. I still have my NO2, and I'm going to have my nucleophile. So this would be the general mechanism of an SNAR. There's one more thing that I want to show you guys, and that's that halogens are special. So if we're looking at an aromatic ring with a halogen, maybe let's look at chlorine. We know that chlorine is electron withdrawing, right? Because it's electronegative. And so we would think that maybe because this is electron withdrawing, that this would activate the ring in the meta position for electrophilic aromatic substitution. But we actually don't see that because the electrons of the chlorine are capable are coming down into the ring, just like an electron donating group. And so even though this is an electron withdrawing, it directs orthopara like an electron donating group because of this resonance structure that we can draw. So this is just kind of one exception to, this is the only exception to the rules where it's an electron withdrawing group that's directing orthopara. And so to summarize, we talked about electron withdrawing groups and how they deactivate the ring through creating resonance with these positive charges. We talked about how electron donating groups activate the ring by pushing electrons into the ring. We talked about electrophilic aromatic substitution. And finally, we talked about SNAR and halogens as an exception to the electron donating, electron withdrawing rules. So today we looked at quite a bit, right? We looked at how resonance can really explain the structure and function and the reactivity of organic molecules. We looked at that in electrophilic aromatic substitution, or Friedel Crafts, and SNAR. Any questions that you have, feel free to drop them down below or visit us at stepsystem.org.